Welcome to the Joy of Architecture. Today we're embarking on a deep dive, and we've got this great stack of sources from one of our listeners. We're going to dig into the core deployment and architecture patterns, the ones really shaping cloud-native and microservices systems today.
Yeah, these sources, they really hammer home that we're in, well, a pretty significant paradigm shift. It's this move away from the old, static, monolithic ways up towards more dynamic, distributed approaches. And it's not just technology for technology's sake. It's being driven hard by business, demands the need for speed, for massive scale, resilience when things break, and just, pure agility.
Okay, let's unpack that because the material makes it super clear. Picking how you deploy, that's not just some technical footnote.
No way.
It's a strategic decision. It hits everything: your velocity, stability, costs, risks. Get it wrong, and, well, things can get tangled up fast.
And what's great here is how the sources give us this comprehensive analysis. It's like a framework, really, to help technical teams make genuinely informed choices. They cover a whole range of patterns you see out there, looking at each one through a consistent lens.
Before we jump into the specific patterns themselves, the guide mentions these foundational principles that a lot of these patterns actually rely on.
Yeah, that's key.
Like automation CI/CD pipelines specifically, they call those absolutely fundamental for getting that speed and reliability.
Exactly. And in these distributed systems, you just need visibility. That's observability, getting good logs, metrics, tracing everything end to end. It's how you figure out what's actually happening inside that spread out system.
Makes sense.
And naturally, security. The sources stress it's got to be baked in right from the start throughout the whole life cycle. DevSecOps, basically.
And it's interesting they stress these aren't just separate ideas floating around.
No, they're linked.
They're interdependent, like building blocks. They say, for example, infrastructure as code, or IAC, is kind of a must-have for doing immutable infrastructure properly.
Right.
And that then makes it easier to do fancier deployment strategies like blue-green.
Precisely.
Yeah.
You often see teams adopting these things progressively. You build the foundation, and that enables the more sophisticated stuff later. They're definitely complementary tools in your toolbox.
Okay, so what's the plan then? We're going to explore what these key patterns are, why you should care about them, how they actually work in the real world. Based on this material, we'll cover immutable infrastructure, infrastructure as code, IAC, blue-green deployment, Canary Release, rolling update, the more traditional multiple services per host, and then the modern standard, service per host or service per container. Let's cut through the noise. First up, immutable infrastructure. The sources define this as, well, an approach where your infrastructure bits servers containers. They're never changed after they go live.
Right? Think of it like stamped cookies. If you want a different cookie, you don't reshape the baked one. You use a different cutter and bake a whole new one.
Okay.
Any change at all config update, new code means you build and deploy totally new instances with that change baked in. Then you get rid of the old ones. It's a big shift from the old way of, SSHing in and patching a running server.
Yeah, I remember those days.
The whole point is getting a consistent, totally predictable state every single time.
So where does this really shine? What are the ideal use cases?
Well, it's fantastic in places needing super high consistency. Finance, healthcare. It clicks perfectly with frequent, predictable deployments from CI/CD pipelines.
Naturally.
And it's almost native to containerized apps, right?
Yeah.
Docker images are immutable. Cloud native loves this. And maybe the biggest draw for some, it makes rollback incredibly simple and reliable.
Okay, that makes sense. So if I find a bug or need a quick security patch, I don't fix the running box.
Nope. You build a brand new clean image that includes the fix, test that image, and then roll it out to replace the old instances.
Instead of trying to patch something that might already be weird or compromised.
Exactly. You're swapping in a verified, clean, secure version built from the ground up. Much safer.
So what are the big wins? Why go through the trouble?
Oh, the benefits are pretty compelling. Security gets a huge boost by never modifying running systems. You drastically shrink the attack surface. Reduces the chance of nasty surprises creeping in from manual changes.
Right.
That immutability also kills configuration drift. So you get way better consistency, better reliability across all your environments. Dev, staging, prod.
Fewer "it worked on my machine" moments.
Hopefully. And that leads directly to fewer deployment failures, more predictable releases. It really enables strategies like blue-green. Troubleshooting gets simpler too. You're diagnosing an issue with a specific versioned artifact, not some unique Snowflake server config. And it plays beautifully with IAC tools, Terraform, CloudFormation, you name it. Boosts automation, helps with scaling.
That reliable rollback sounds amazing. But come on, it can't be perfect. What are the downsides, the catches?
Oh, definitely catches. Building and deploying fresh images every time can, potentially slow down your build deploy cycle, though good automation helps a lot there.
Okay.
You might see higher resource used temporarily, especially with blue-green, running two full stacks side by side for a bit.
Right, the cost.
Yeah. And a big one, especially if you're retrofitting older apps, is state management. Anything persistent user sessions, database data has to live outside the instance.
Needs to be externalized.
Totally. Dedicated services like AWS DynamoDB, Azure SQL, S3, blob storage. This often means you need to re-architect your application to handle state that way.
That sounds like potentially a lot of work.
It can be. Plus, there's a real learning curve, a mindset shift for teams used to the old mutable world. And honestly, it's not always easy to apply this to legacy apps, especially really stateful ones, without some serious refactoring.
So, for a lot of existing applications, that state management piece is the main hurdle to adopting this pattern.
Absolutely. Your app basically needs to assume its instances are disposable, that they could vanish any second, and the important stuff is safe somewhere else.
How do people actually do this in the cloud? What services get used?
All the big players support this. AWS, you're looking at CloudFormation or Terraform for the IAC Foundation, AMIs for virtual machine images, or ECEKS for containers. Code pipeline, code build handle the CI/CD automation.
Okay.
Things like dynamic config, secrets, they live externally in parameter store or secrets manager. The typical flow, build images with Packer for VMs or Docker for containers, stash them at a registry like ECR or an AMI registry. Then your CI/CD pipeline uses IAC tools to spin up new infrastructure from those images.
And Azure GCP, similar story.
Pretty much. Azure uses ARM templates, Bicep or Terraform for IAC, VMs or AKS for the compute, Azure DevOps for CI/CD, ACR for container images, GCP has Deployment Manager or Terraform, GCE or GKE, Cloud Build, GCR or Artifact Registry.
And the key DevOps tools that keep popping up alongside this pattern.
Your core IAC tools, Terraform, Pulumi. Packer's common for VM images, Docker, obviously, for container images. Orchestrators like Kubernetes are basically designed around managing immutable containers. And CI/CD platforms, Jenkins, GitHub Actions, GitLab CI, Spacelift, they automate that whole build-to-deploy pipeline. Config management tools like Ansible or Chef may be used during image creation, but generally not for touching running instances.
Got it. The workflow described in the sources sounds like code commit, kicks off the CI pipeline, it builds a version thing VM image, container image sticks it in a registry, then, often using IAC, it provisions a new environment or instance set using that artifact. Automated tests run. If it passes,
Traffic gets shifted.
traffic gets shifted to the new stuff, and finally, the old stuff gets torn down.
That repeatable workflow is critical. And the operational win on rollback, it's huge. If the deployment goes sideways after the traffic switch, you just point traffic back to the previous known good immutable instances. It's fast, super reliable, and avoids all the messy complexity of trying to undo changes on a live mutable system.
Monitoring must change focus too, right? If instances are just cattle disappearing all the time, you can't log into the box to check logs.
Exactly. The focus shifts. You monitor the new instances as they spin up, and you monitor the health of the deployment pipeline itself. Centralized logging and metrics aggregation become non-negotiable. Logs have to be shipped off the instance before it gets terminated. You track things like pipeline success rates, how long deployments take, and the overall health metrics of the new group of instances.
What about drift detection? The whole point is drift shouldn't happen, but the sources mention it.
Yeah, the principle is designed to prevent drift because you ban in-place changes. But, you still need ways to detect if someone does manage to make an unauthorized manual change, maybe bypassing the process. Tools can compare the live state to your IAC definition. But honestly, the primary defense is just strict adherence to the rule. Changes only happen by deploying new instances.
And patching. Security updates.
Handled the same way. Build new base images with the patches. Rebuild your application images on top. Roll out the updated instances. Secrets management, again, absolutely critical. Never, ever bake secrets into images. Use dedicated secret stores. Inject them securely at launch or runtime.
Okay, so best practices. Full automation, version control everything code, infrastructure definitions, image build scripts, externalize all your mutable state, aim for small, frequent releases, have comprehensive automated testing, embrace IAC, use containers. What are the big no-nos, the
The
anti-adders?
absolute killer,
Right.
making manual in-place changes after deployment. That one act just blows up the whole principle, brings back drift, inconsistency.
Right.
Other big ones, not versioning your images or artifacts properly, baking secrets into images, huge security fail, creating massive monolithic images that just clog up your pipeline, and neglecting centralized logging and
Yeah.
external monitoring. You'll be flying blind.
The sources mentioned Netflix, Spotify, Pinterest as heavy users. Netflix was way ahead of the curve, right? Using AMI's Spinnaker, their red-black deployments.
Yeah, they pioneered a lot of this at scale. And generally, industry experience backs up the benefits. Smoother rollbacks, better security posture, predictable reproducibility. But it also highlights the challenges that cultural shift needed in teams, the need for really solid automated testing, especially when you're migrating existing stuff. It's a big upfront investment in process and tools, no doubt. But for companies operating at scale, the stability and agility payoffs are massive. It really demands discipline. Powerful pattern, though.
That's a solid look at immutable infrastructure, and it feels like it flows right into our next pattern. Infrastructure as code, or IAC, this is all about managing and provisioning your actual infrastructure, networks, VMs, load balancers, the whole topology using code, basically, treating your infra like software.
Exactly right. You define what you want your infrastructure to look like, the desired state, in configuration files, in code. That code then gets version controlled, tested, and used to repeatedly reliably stand up or modify your infrastructure. It's bringing software engineering discipline to the world of infrastructure.
So instead of clicking around in a web console, you're writing code that builds your cloud environment.
Pretty much. You define the what in your code files, and then a tool takes that definition and talks to the cloud provider's APIs to make it happen. This is obviously perfect for cloud environments because they're API driven.
Makes sense.
It's absolutely central to DevOps practices enabling automation, fast iterations. It's crucial for managing complex setups consistently across different environments, like dev, staging, and prod. Vital for scalable systems, allowing you to spin up resources quickly and reliably. It's a key piece for disaster recovery. You can recreate your infra fast, and it gives you a clear audit trail for every change, which helps with compliance. It fosters collaboration, too, because the infra definition is right there in code, easy to share and review.
So what are the biggest advantages driving people to IAC?
Automation and speed are massive. Provisioning infrastructure becomes incredibly fast and repeatable. You can duplicate entire environments quickly. This naturally leads to consistency and standardization. It virtually eliminates configuration drift between environments.
Nice.
You get full version control and change management through Git history, audits, easy rollbacks. It can definitely lead to cost reduction by helping optimize resource usage and cutting down on manual effort. Risk goes down because you minimize human error, and you can actually test your infrastructure changes before applying them live.
Testing infra changes, how does that work?
Tools often have a
Oh.
plan or preview step where they show you exactly what they intend to change before they do anything. Plus, there are testing frameworks specifically for IAC. It really boosts collaboration too, making the infra definition visible and understandable, promoting that developer mindset for infrastructure. And obviously, it enables easier scalability.
So fundamentally, it's just way more reliable and faster than clicking buttons manually.
Absolutely. Connecting it back, it makes your infrastructure setup as predictable and repeatable as your application build process.
Okay, but what are the trade-offs? It can't be all sunshine.
No, definitely not. There's a learning curve for sure. New tools, new languages like HCL for Terraform or YAML for CloudFormation, and new principles to grasp. The tools themselves can get complex, especially around managing state for declarative tools.
State, what's that?
Declarative tools need to keep track of the infrastructure they manage. That state file becomes critical. Managing it properly, especially in teams, requires care. Initial setup takes time and investment. State management, as I said, is crucial and needs a secure remote place to live to avoid corruption or conflicts.
Okay.
Tools might have limitations, maybe not supporting the very latest cloud features immediately. And security risks are real. If you accidentally hardcode secrets in your IAC files or give the IAC tool way too many permissions, you've created a vulnerability. The source is really stressed. IAC isn't just adopting a tool, it's a cultural shift towards software-defined infrastructure.
Implementations in the cloud, we're talking native services like AWS CloudFormation, Azure ARM templates or the newer Bicep language, GCP deployment manager.
Yep, those are common. And multi-cloud tools like Terraform are hugely popular too. You also see config management tools like Ansible, Chef, Puppet used, but often after IAC provisions the base infrastructure to configure software inside those VMs or instances.
Right, the layering.
Exactly. And there's that important distinction. Declarative tools like Terraform, CloudFormation, Pulumi, you define the end state, the tool figures out how to get there. Versus imperative tools like Ansible, Chef, or just plain scripts, you define the sequence of steps. Many teams end up using a mix.
The workflow the sources describe sounds really important. Write or update your ISC code, commit it to Git, a CI/CD pipeline triggers. The ISC tool initializes, it generates a plan or preview showing the intended changes.
Super important step.
Maybe some static analysis or policy checks run on that plan, maybe a manual approval gate. Then the tool applies the changes via cloud APIs. And finally, it updates its state file, ideally stored securely somewhere remote.
That plan stage is gold. It lets you see the blast radius, understand the impact before you hit apply. The key diagram elements are always the developer, the code repo, VCS, the CI/CD pipeline orchestrating things, the IAC tool itself talking to the cloud, and that secure remote state file tracking what's actually been built.
Operationally, what are the big things you need to keep an eye on with IAC?
State management. Number one for declarative tools. Using a secure remote backend like S3 with DynamoDB lock-in on AWS, Azure Blob, GCP storage is best practice for teams. Prevents conflicts, keeps it safe, challenges. State can get corrupted, or it can drift from reality if manual changes sneak in.
And rollback.
Typically, you revert the code change in Git to a previous working commit, then rerun your IAC tool. It figures out how to change the infrastructure back to match that older code definition. Monitoring needs to cover both the infrastructure health and the health of your IAC pipeline runs. Are they succeeding? Failing?
Drift detection again. Seems to be a theme.
Yeah, because manual changes are the enemy of consistency. Even with IAC, someone might bypass the process. So you need tools or processes to compare the live state against your code definition. Things like Terraform Plan, dedicated tools like Drift Collar, or built-in features in platforms like Spacelift can help spot drift. Remediation. Usually reapply the IAC code to force reality back into line with the desired state.
Secrets.
Never ever hardcode them in IAC files. Use proper secret management tools, Vault, Secrets Manager, Key Vault. Retrieve them dynamically or inject them securely at runtime. And modularization is key for managing complexity as your IAC code base grows. Break things into reusable chunks like a standard VPC setup or a Kubernetes cluster configuration.
Okay, best practices. Version control everything. Prefer declarative tools. Ensure your code is idempotent. Running it multiple times has the same effect. Modular design. Secure your state and secrets properly. Automate testing, linting, static analysis, maybe integration tests. Integrate IAC into CI/CD. Use clear naming and tagging. Implement policy as code. Review and refactor your IAC regularly. And use least privilege for the tools.
And the anti-patterns are basically doing the opposite. Manual changes are the cardinal sin, causing drift. Hard-coding secrets, huge risk. Not using version control chaos. Monolithic configs. Ignoring state or using local state files in a team. Only using IAC for the initial setup. Skipping automated testing. Giving your IAC tool admin rights to everything. Treating IAC like an afterthought. All bad news.
The sources mention companies building sophisticated platforms around IAC and just widespread adoption driven by reducing errors, enabling scale, getting traceability.
Yeah, it's foundational now.
Yeah.
But the common challenges remain. That learning curve, the complexities of state, the security implications, it really forces you to think about infrastructure with software engineering discipline. The culture shift is as important as the tools.
That's a perfect bridge to deployment strategies that ISC really enables. Let's talk blue-green deployment.
Yeah.
The idea is you have two identical production environments, right? Blue and green.
Yeah, the source defines it pretty clearly. Your current live version, V1, is running the blue environment, taking all the user traffic. Then you stand up a completely separate identical environment called green and deploy your new version, V2, onto it.
Identical is the key word there.
Absolutely. You thoroughly test V2 in that isolated green environment. Once you're happy, you flip a switch, usually at the load balancer or DNS level, and instantly redirect all live traffic from blue to green. V2 is now live.
And the goal is basically zero downtime and lower risk.
Exactly. It's great for apps where downtime is a killer, where you absolutely need a fast, reliable rollback option. Ideal for high-risk releases where you want to test extensively in a production-like setting before exposing it to everyone. Works well if you need to coordinate infra and app updates together. And generally, it's easiest to pull off for stateless applications.
The big wins seem obvious. Minimal or zero downtime, because that traffic switch is usually super fast. Massively reduced risk. And that instant rollback if V2 misbehaves after the switch, boom, you just point traffic straight back to the stable V1 in blue. Gives you a lot of confidence in releases and allows really thorough testing in that identical green environment.
That instant revert capability is often the deciding factor for critical systems.
Running two identical production environments side by side, that sounds expensive.
That's the number one trade-off. Infrastructure costs. You're essentially doubling your compute, maybe more, during the transition period.
Ouch.
And the complexity around state management and database synchronization, that's often the biggest hurdle, especially for stateful apps. You need really careful planning for database schema changes, backward compatibility is key, or you need robust data replication strategies, or maybe complex multi-phase migration patterns like expand and contract. It's not trivial.
Right. Keeping data in sync or compatible across two live versions sounds tricky.
It is. You can also hit issues with long-running user sessions or transactions getting interrupted during the switch. It's resource-intensive, obviously. The traffic switching mechanism itself needs careful design and testing, and the whole process, provisioning and testing green, can potentially take longer overall than, say, a rolling update. The source really emphasizes that getting those environments truly identical is especially hard when persistent data is involved.
How do people typically implement this in the cloud?
Cloud platforms have features to help. AWS Elastic Beanstalk has built-in clone and swap C&M functionality. AWS Code Deploy can manage blue-green for EC2, ECS using ALB target groups or Lambda aliases, Route 53 for DNS switching, ALB and LB for routing. IC tools are pretty much essential here to ensure those environments are identical.
And Azure, GCP.
Azure App Service has deployment slots, which are perfect for this. In AKS, Kubernetes, you'd manage two distinct sets of deployments and services, using ingress controllers or service selectors to switch traffic. Azure DevOps can orchestrate the whole flow, Traffic Manager or Front Door for global switching. GCP offers App Engine traffic splitting, managing two resource sets in GKE with LB ingress switching, or using cloud DNS and load balancing.
What about the DevOps tools side?
Kubernetes is often the foundation, but you need tooling or careful configuration on top to manage the two separate deployments in the traffic switch, as its default is rolling update. Helm charts can help manage the release definitions for blue and green. CI/CD platforms Jenkins, Spinnaker, GitHub Actions, GitLab CI orchestrate the provisioning, deployment, testing, and switching steps. And service meshes like Istio or Linkerd provide really fine-grained control over that traffic routing for the switchover.
The workflow diagrams usually show blue V1 is live. You spin up green, V2, test green thoroughly. Then the big moment, switch traffic, monitor green like crazy now that it's live, and then you either keep blue around for a bit as a hot standby for rollback, or you decommission it to save costs. The database handling is always shown as a critical, often complex part of that picture.
Operationally, the huge plus is that fast, simple rollback. Just point traffic back to blue. Minimizes your recovery time, MTTR. Monitoring is absolutely vital for both environments. Test green rigorously before the switch, then watch it like a hawk afterwards. Track errors, latency, resource use, key business metrics. Comparing green's performance against the blue baseline is crucial.
Those database migrations still sound like the scariest part for stateful apps.
They absolutely are the most complex piece. Common strategies include using a shared database, but only making backward compatible schema changes. Or setting up replication and synchronization, but you have to manage lag and consistency carefully. Or using more complex patterns like expand and contract for breaking changes, which involves multiple deployment steps. Sometimes putting the app in a temporary read-only mode during the switch is an option.
Cost management means automating the teardown of that old blue environment quickly. Configuration consistency relies heavily on using IAC properly. Session management needs thought. How do you handle users with long sessions during the switch? And you absolutely have to make sure the green environment is warmed up, caches loaded, connections pooled before you throw full production traffic at it.
Best practices. Automate everything. Use IAC religiously for consistency. Test green comprehensively, monitor intensely, compare performance, plan those database migrations meticulously, keep the actual switchover time as short as possible. Warm up green. Have a crystal clear tested rollback plan.
And the anti-patterns to avoid. Manually creating environments recipe for inconsistency. Skimping on testing green defeats a whole purpose. Keeping blue running forever burns money. Ignoring database compatibility or sync issues guaranteed failure for stateful apps. Doing a hot switch to a cold green environment performance tanks, maybe outages, and accidentally letting some traffic bleed over to green before you intend to.
Case studies often mention Netflix's red-black approach using Spinnaker. Amazon often favors blue-green for critical e-commerce stuff, where that instant rollback is paramount. Etsy, Spotify use it too. Generally, industry sees it as faster for the deployment event itself than Canary, but higher cost. One study mentions slightly higher failure rates than Canary, interestingly, but both offer that crucial rollback safety net. The complexity really shifts to managing the data state effectively.
It really highlights that trade-off. Speed of cutover and instant rollback versus cost and data complexity. How does it stack up against Canary Release? That seems to tackle risk in a very different, more gradual way.
That's a perfect comparison the sources draw out. Canary Release is fundamentally different. You release the new version, the Canary, to only a tiny fraction of your users or servers first, like 1%, 5%.
Okay.
Then you watch it like a hawk. Monitor its performance, errors, business metrics, comparing it directly against the stable version everyone else is using. If the Canary looks healthy, behaving well,
You gradually give it more traffic?
exactly. You slowly dial up the percentage, maybe 10%, 25%, 50%, 100%, monitoring carefully at each stage.
Like the coal miners sending a canary down the shaft first.
Precisely the analogy. If the Canary version starts failing or showing problems, you know about it early, while the impact is still limited to that small group. You pull it back immediately before it affects everyone. The goal is minimizing the blast radius of a potentially bad release.
So where is Canary ideal?
It's fantastic when you want to gather real-world feedback from actual users on a new version.
Yeah.
Great for high-risk or high-impact changes where containing potential failure is critical. Perfect for teams doing frequent updates via continuous delivery as it manages the risk of each small release. Useful for A/B testing features or performance tweaks. And excellent for validating complex changes empirically in the wild, but safely.
The benefits sound heavily focused on risk management and learning.
They really are. You get significant risk reduction. That limited blast radius is key. You get real-world testing and early feedback, catching issues you might miss in staging. It supports faster iteration and CD because each release feels less risky. You get live performance monitoring, comparing the new directly to the old baseline. There's zero or minimal downtime for the vast majority of users. Promotion or rollback decisions become data-driven based on metrics, and it even gives you a small-scale capacity test initially.
What strikes me here is how incredibly dependent this must be on top-notch, real-time monitoring and analytics.
Absolutely critical, and that dependency is also where some trade-offs lie. Compared to simpler strategies, the implementation complexity is definitely higher. You need sophisticated traffic splitting capabilities, version management, smart routing.
Right.
The monitoring and alerting overhead is significant. You need granular, real-time data pouring in, well-defined thresholds, automated alerting, maybe even automated rollback triggers. The overall deployment time can stretch out because of those phased rollouts and the monitoring periods you need at each step. There are infrastructure costs for running those Canary instances alongside the stable fleet.
And having multiple versions live at once must add complexity too.
It does. You have to ensure API and data schema backward compatibility between the stable and Canary versions. Database schema changes need careful handling, just like with blue-green often requiring backward compatibility or using feature flags. It can sometimes be hard to pin down really subtle bugs that only show up at massive scale. And there's a small potential for user experience fragmentation, though usually mitigated by keeping the Canary phase short or targeting specific user groups.
How do the cloud platforms and tools support this?
They have various capabilities. AWS CodeDeploy does Canary for EC2, ECS, Lambda using weighted aliases. ALBs can do traffic weighting. API Gateway has Canary stages. Route 53 weighted DNS. Azure App Service has testing and production slots. In AKS, service meshes like Istio or Linkerd are very common for fine-grained traffic routing based on percentages or headers. Progressive delivery operators like Flagger or Argo rollouts automate the metric analysis and promotion rollback. Application Gateway can do weighted routing. GCP Cloud Run offers native gradual rollouts. GKE leverages meshes and operators heavily. And GCP Cloud Deploy provides managed pipelines with built-in Canary support. On the DevOps tool side, service meshes, Istio Linkerd, are almost essential for the sophisticated L7 traffic control and observability needed. Progressive delivery operators, Flagger, Argo rollouts, are huge for automating the analysis and decision-making. Future flag systems, LaunchDarkly, Optimizely, etc., are often used with Canaries to separate feature releases from code deployments. CI/CD orchestrates it all. And comprehensive monitoring observability tools, Prometheus, Grafana, Datadog, ELK, Jaeger, Zipkin, are absolutely non-negotiable for collecting the data to judge the canary's health.
The workflow sounds like stable v1 is live, deploy v2 as a small canary, route a tiny bit of traffic, say 15% to v2, using load balancer weights or mesh rules. Monitor v2 intensely metrics, logs, traces, comparing it constantly to v1. Analyze the data. Is it healthy? If yes, gradually increase traffic 10%, 25%, etc., monitoring at each stage. If no, roll back immediately by shifting traffic back to v1. If it gets to 100% successfully, v2 becomes the new stable and v1 gets decommissioned.
Operationally, rollback is fast. Just adjust the traffic weights back to V1. Automated rollbacks triggered by monitoring alerts showing bad metrics are highly recommended. Tools like Swagger specialize in this automated analysis and rollback. Monitoring, as we've said, is everything. Technical metrics, latency, errors, business metrics, conversions, engagement. Baseline comparison to V1 is key. Robust alerting, logging, and tracing for digging into issues. Traffic management needs that sophisticated L7 control.
Defining that initial canary group, the size, who gets it, that seems important too.
Critical. Small enough to limit impact, 1 to 5% often, but large enough to get statistically meaningful data. How long you stay at each percentage point also matters. Need enough time to gather data, spot slower burning issues. Session affinity might be needed for user experience consistency. And automated canary analysis tools can take this further, automatically comparing metrics against thresholds and deciding to promote or roll back without human intervention.
Best practices. Automate the rollout and rollback. Define clear, measurable metrics and thresholds for success failure. Start with a very small group. Monitor continuously, compare rigorously, use feature flags. Ensure comprehensive observability. Test your rollback mechanism. Increase traffic incrementally. Segment users strategically if needed.
Anti-patterns. Blind canaries rolling out without proper monitoring. Vague success criteria. Starting with too large a group defeats the safety purpose. Ignoring user feedback or business metrics, relying on slow, manual rollbacks, not handling DB or API compatibility issues between versions, having monitoring periods that are too short.
Sources mention Netflix again with their sophisticated canary process, using automated analysis like Kayenta, Google's Chrome Canary channel, Cloud Deploy, Mozilla Firefox's nightly beta channels.
Yeah, industry experience suggests Canary often leads to lower failure rates and less user impact than blue-green, because of that gradual feedback loop. But the trade-off is potentially longer overall deployment times. It's very data-driven, requires sophistication in monitoring and analytics, pushing towards AIOps territory. It's about balancing innovation speed with stability.
That's a great overview of Canary. Now let's talk about what many consider the workhorse pattern, especially in orchestrators. Rolling update. The sources define this as gradually introducing a new version by updating existing instances or pods, but in batches.
Right, it's a phased replacement strategy. The orchestrator starts bringing up instances with the new version, checks if they're healthy, adds them to the pool, and then gracefully terminates instances running the old version. So for a period, both V1 and V2 are running concurrently and serving traffic. The goal is to maintain overall service capacity and availability throughout the update.
And this is often the default setting in tools like Kubernetes.
It is. It's the standard deployment strategy in Kubernetes deployments and Docker Swarm services. It's great for achieving zero or minimal downtime, especially for stateless applications where temporary inconsistencies are less problematic. It's more resource efficient than blue-green because you don't need that full duplicate environment. And it's well suited for frequent, lower-risk updates.
The benefits seem clear. Minimal or zero downtime if done right. A gradual rollout, which offers some risk reduction compared to replacing everything at once. You can potentially stop early if things go bad. It's resource efficient. Rollback is relatively simple if you catch problems early, usually involves just telling the orchestrator to roll back, which triggers another rolling update using the previous version. And it's widely supported, often the default.
It hits a sweet spot for many common use cases, offering a decent balance of safety and efficiency.
But trade-offs exist. It's definitely slower than an instant cutover like blue-green.
Yeah.
And that period where you have mixed versions running side by side.
That's the big one. That mixed version state is the major potential pitfall. If your new version has breaking API changes or incompatible database schema expectations or just behaves differently in a way the old version or other services talking to it can't handle, you will run into errors during that transition period. Rollback, while possible, isn't instant. It's basically doing another rolling deployment, but this time bringing back the previous version. That takes time. Depending on how you configure it, like the max unavailable setting in K8s, you might see a temporary dip in overall capacity.
Yeah.
And it's hard to fully test the new version in isolation under real production load before it starts mixing with the old version live. The sources really stress. Success hinges on application version compatibility and having robust health checks.
How is this typically implemented in the cloud?
It's built right into the container orchestrators. AWS ECX via K8s deployments, Azure AKS, GCP, GKE all do this natively. AWS CoDeploy supports it for EC2 and ECS2. Azure App Service has gradual rollout options that function similarly. GCP App Engine supports it. Even CloudFormation can manage rolling updates for things like EC2 auto-scaling groups. The key DevOps tools are the orchestrators themselves. Kubernetes controls it with the max surge, how many extra instances you can create, and max unavailable, how many can be down, parameters and deployments. Docker Swarm has similar controls like update delay, update parallelism. Helm charts usually just leverage the default Kubernetes rolling update. CI/CD platforms trigger these updates.
The workflow sounds like V1 instances are running. You trigger the update to V2. The orchestrator starts creating V2 instances in batches, respecting max surge. It runs health checks on these new V2 instances. As they become healthy and join the load balancer pool, the orchestrator starts terminating old V1 instances, respecting max and available, ensuring they shut down gracefully. This repeats batch by batch until all V1s are replaced by V2s.
And those health checks you mentioned, absolutely critical. Readiness probes, liveness probes in Kubernetes, health checks in Docker Swarm. They prevent bad new instances from getting traffic, and they make sure old instances aren't killed off before the new ones are ready to take over. They are the safety mechanism.
Operationally, rollback is usually an orchestrator command kubecle rollout undo for K8s, which triggers that reverse rolling update back to V1, not instant. Monitoring means watching the health and performance of the new instances as they join, tracking overall service metrics, errors, latency, and keeping an eye on resource usage to make sure capacity stays sufficient during the churn.
Yeah, those health checks need to be accurate and meaningful. Version compatibility is the big headache. Due to that mixed state APIs, data schemas need to be backward compatible during the rollout. For breaking changes, you might need more complex multi-step strategies. Tuning those parameters like max surge and max unavailable is about balancing deployment speed against risk and capacity impact. It's designed for minimal downtime if you get the health checks, parameters, and graceful shutdown right.
Best practices. Implement robust, accurate health checks. Configure max surge max unavailable appropriately. Ensure backward compatibility. Monitor key metrics during the rollout. Automate the whole process. Implement graceful shutdown in your app code. Maybe start with smaller batches for risky changes. Test your rollback procedure.
Anti-patterns. No health checks, or really poor ones, high risk of widespread failure. Being too aggressive with max unavailable, causing capacity dips. Ignoring version incompatibilities, leading to errors when V1 and V2 interact. Not monitoring during the rollout. Doing manual rolling updates error-prone doesn't scale. Not having graceful shutdown, causing lost requests or data issues.
Case studies often just point to the fact that it's the Kubernetes default strategy, used by literally countless organizations for routine updates. Docker Swarm users leverage its native capabilities too. It's the standard go-to for many stateless microservices.
It's often perceived as the simplest option, especially with orchestrators handling the mechanics. But the sources rightly point out that this apparent simplicity hides the critical need for careful planning around version compatibility and the absolute necessity of effective health checks. Don't underestimate those aspects.
Okay, moving to something that feels a bit more traditional, maybe less aligned with modern microservices. Multiple services per host. This is running different services, maybe multiple instances, all crammed onto a single server or VM, sharing the OS and hardware.
Yeah, this was pretty much the standard way before containers really took off. You'd have distinct processes running maybe a web server, an app server, a database, all on one machine. Or sometimes multiple apps running inside a single shared process, like different WAR files deployed to the same Tomcat server.
Where might you still see this, or where was it ideal?
Well, for resource-constrained environments, definitely. If you need to squeeze maximum utilization out of fewer VMs to save costs, often used in dev test environments where strong isolation isn't the absolute top priority. Maybe for smaller, simpler applications or during the very early stages of breaking down a monolith. Could work for very lightweight services that don't consume many resources. And of course, legacy systems that were built this way and are hard to change. Also, if you have a very homogeneous stack where all services use the same tech and dependencies, the risk of conflict is lower.
So the main driver is resource efficiency, basically packing more onto less hardware.
Exactly. You share the OS, the hardware, potentially runtimes. Theoretically, better utilization, fewer idle resources compared to giving every tiny service its own VM. Deployment could be rapid in very simple cases, just copy files, start a process, initial infra costs might be lower, and networking between services on the same host can be simpler using IPC or localhost, maybe lower latency.
But this feels like it clashes hard with microservice principles. What are the big downsides? The trade-offs?
Oh, they're significant. The biggest is poor isolation. You have the classic noisy neighbor problem. One badly behaving or resource hogging service can starve or crash others on the same host.
Right.
There's resource contention and unpredictability. It's really hard to guarantee performance or enforce strict resource limits per service without getting deep into complex OS-level controls like cgroups manually. Dependency conflicts are a nightmare. Services might need different versions of shared libraries, runtimes, or even try to bind to the same network port. Huge risk there.
Yeah, dependency hell.
Totally. Deploying and configuring multiple diverse services and all their different dependencies onto one shared host gets complex fast. Scaling is inefficient. If one service needs more resources, you often have to scale up the entire host, benefiting or burdening all the other services too.
Yeah.
Maintenance gets risky. Patching the OS or updating a shared runtime affects all services at once. And visibility. Monitoring is tough. It's hard to accurately track resource usage per individual service, especially if they're inside a shared process like a JVM.
It really sounds like containers were invented specifically to solve most of these problems while still letting you run multiple things on one host.
Pretty much. Containers give you that crucial process and dependency isolation, resource limiting capabilities, and standardized packaging, addressing the main weaknesses of this traditional pattern while still allowing density.
Real-world examples are like those traditional on-prem setups. A single server running Apache, Tomcat with multiple apps, and MySQL. Or shared Java app servers. In the cloud, it's like spinning up one big EC2 or Azure VM and just manually installing and running several different services on it using scripts.
The DevOps tools often seen here are config management tools like Ansible, Chef, Puppet, used to configure the services on the host. Monitoring focuses on host-level metrics, Nagios, Zabbix, Node Exporter, or process-level tools as top. APM tools can help trace within co-hosted services. Deployment might be custom scripts run by Jenkins or similar. And reverse proxies like Nginx or Apache are common to route incoming traffic to the right service on the right port.
The diagrams usually show one big host box, an OS layer inside, and then multiple service boxes sitting on the OS, sharing CPU, memory, etc. The workflow is often manual or script-heavy. Provision the host, install shared stuff, deploy each service individually, configure the proxy, set up monitoring.
Operationally, rollback is often manual or script-based too. Stop the new process, restart the old one. Can be slow, error-prone, might need downtime. Monitoring, as we said, is challenging for individual services. Resource management is tough services compete, hard to enforce quotas. Capacity planning needs to be conservative, accounting for the combined peak load.
Dependency management sounds like the biggest headache.
It's a constant battle, high risk of conflicts. A change for one service breaks another. Needs meticulous planning and testing of the whole co-hosted group. Security isolation is weak too. A vulnerability in one service could potentially compromise others or the whole host much more easily than with VMs or containers. And patching the OS or shared runtimes is an all-or-nothing affair, affecting everything simultaneously. Requires coordinated downtime or very careful planning.
So best practices here are more like mitigation strategies or steps towards a better pattern.
Exactly. Things like, if you must co-host, try to standardize runtimes and dependencies as much as possible. Test the combined services thoroughly together before deployment. Implement comprehensive host-level monitoring and alerting. Be very careful and conservative with capacity planning. Use reverse proxies. Automate configuration management. Keep good backups. And, importantly, actively consider migrating towards containers for better isolation and manageability.
And the anti-patterns. Co-hosting wildly different tech stacks or services with opposite resource needs, having no resource monitoring, ignoring dependency conflicts until things break, overloading the host, manually configuring everything, treating the host like a unique pet instead of replaceable cattle.
Case studies include traditional shared web hosting, maybe very small startups, prioritizing initial cost savings, legacy apps, and sometimes the self-hosting community, though even there, Docker or virtualization is increasingly recommended. The bottom line from the sources is, while it might seem resource efficient up front, the lack of isolation, scaling challenges, and operational complexity make it a poor fit for modern microservices where resilience and independent agility are paramount. The operational risks usually outweigh the cost savings for anything critical or large scale. It's often a legacy situation, not a target architecture.
Which perfectly sets up the final pattern the sources cover, the one that's really become the standard for modern microservices. Service per host, or more commonly now, service per container. Each service instance gets its own dedicated, isolated environment.
Right. The definition includes two main flavors. Service instance per VM. Each service instance is packaged and deployed as its own complete virtual machine. Provides strong OS-level isolation, but can be heavy. Then there's service instance per container. Each service instance is packaged as a lightweight container image, like Docker,
Yeah.
and runs in its own isolated container process. You can run multiple isolated containers on a single underlying host, VM or physical. This is far more prevalent for microservices today because it offers a great balance of isolation and efficiency.
And this is considered pretty fundamental for doing microservices properly.
Absolutely. It's a core enabler. It gives you independent deployment teams can release their services without impacting others. Independent scaling scales service A without affecting service B. Fault isolation, if service C crashes, it doesn't bring down the whole host or unrelated services.
Makes sense.
It's ideal when you need that strong isolation, preventing noisy neighbors and containing failures. It lets teams choose the best tech stack for their specific service, as dependencies are neatly encapsulated in the container. Essential when services have vastly different scaling needs. Enhances security by limiting the blast radius. Allows precise resource management via orchestrator controls, CPU memory limits. And it's key for building resilient, fault-tolerant systems because failures are contained, and orchestrators can automatically restart failed instances.
The benefits are clear. Strong isolation, independent scaling, precise resource control, no dependency conflicts. And the container version adds portability, faster startup, higher density.
Exactly. Containers really hit the sweet spot, providing most of the isolation benefits of VMs, but with much lower overhead, allowing you to pack more services onto your infrastructure efficiently. They directly address the main pain points of the multiple services per host approach.
But if you have potentially hundreds, even thousands of these little isolated containers running around, managing all that must get complicated.
That is the primary trade-off, and it's a big one. The operational complexity skyrockets. You simply cannot manage that many individual units manually. This pattern absolutely requires a sophisticated orchestration platform, Kubernetes being the prime example to handle deployment, scaling, networking, health checking, etc.
Right, you need automation.
You do. Inter-service communication also becomes more complex. Services can't just talk via local hosts easily. They have to communicate over the network using APIs. This means you need robust mechanisms for service discovery, routing, resilience, often leading to things like API gateways or service meshes. And there's definitely an initial setup time and investment needed to get the orchestration platform running, establish solid CI/CD pipelines for building and deploying container images, and set up standardized image creation processes.
Where do we see this implemented? Which cloud services?
It's all about the container orchestration services. AWS EKS, Kubernetes, Azure AKS, GCP GKE are the big three managed Kubernetes offerings. AWS ECS is another very popular container orchestrator. If you were doing per VM, you'd use standard EC2, Azure VMs, GCE. And then there are serverless container platforms like AWS Fargate, Azure Container Instances, ACI, or GCP Cloud Run, which abstract away the underlying host management entirely, further simplifying operations for the container variant. Key DevOps tools. Docker for containerization is fundamental. Orchestration platforms, Kubernetes is dominant. Docker Swarm still exists. CI/CD pipelines are essential. Jenkins, GitHub Actions, GitLab CI, Spinnaker, cloud provider pipelines. IC tools, Terraform, CloudFormation, etc., are used to provision the underlying cluster infrastructure or hosts. Image registries, Docker Hub, ECR, ACR, GCR store the images. And service discovery tools like Core DNS and K8s, Console, and service meshes, Istio, Linkerd, become crucial for managing how services find and talk to each other reliably and observably.
The typical workflow for service per container sounds like developer writes code, builds a container image using a Docker file, pushes that versioned image to a registry. Then they update the orchestrator's configuration, like a Kubernetes deployment YAML file, specifying the new image version. The orchestrator notices the change, pulls the new image down to the worker nodes, creates new container instances, pod tasks, usually using a controlled rollout strategy like rolling update by default, or maybe a configured blue-green or canary. The load balancer or service mesh updates its routing to include the new healthy instances. And the orchestrator just keeps managing the whole fleet, handling health checks, scaling based on load, restarting failed containers. The orchestrator is the brain.
Operationally, rollback is usually handled by the orchestrator too. In Kubernetes, kubical rollout undo tells it to deploy the previous known good image version, again, typically using a rolling update. It's generally fast, especially if your container images are reasonably small. Monitoring becomes absolutely critical. You need distributed tracing to follow requests across services, centralized logging to capture output from ephemeral containers, and detailed metrics per service instance. Aggregation tools like Prometheus, Datadog, Splunk, ELK are essential. You also need to monitor the health and resource usage of the orchestrator itself and the underlying worker nodes.
But scaling gets much better, right? More granular.
Huge advantage. Scaling is independent per service. You can configure the orchestrator to automatically scale a specific service up or down based on metrics like CPU usage, memory pressure, or even custom application metrics, using features like Kubernetes Horizontal Pod Autoscaler, HPA. State management, though, still needs to be externalized, just like with immutable infrastructure. Databases, caches, object storage handle the persistence because containers should ideally be stateless and disposable. Configuration gets injected at runtime config maps, secrets in Kubernetes never baked into the image itself. Patching. Build a new image with the updated base OS or dependencies, push it until the orchestrator to deploy it.
So the main operational challenge boils down to managing that inherent complexity of a distributed system with many moving parts.
Exactly. Successfully running this pattern at scale requires sophisticated operational practices, heavy automation, and skilled teams who understand distributed systems concepts.
Best practices. Leverage your orchestration platform's features fully. Automate your build and deployment pipelines completely, CI/CD. Implement robust monitoring and observability logging, metrics tracing per service. Externalize all state and configuration. Standardize your container image creation process. Docker file best practices, keep images small. Implement automated scaling policies. Use service discovery and potentially a service mesh. Secure your images and the container runtime environment. And version control everything: your application code, your Docker files, your orchestrator configuration manifests.
Anti-patterns to avoid. Trying to manage containers manually at scale, just impossible. Baking configuration or secrets directly into images, insecure and inflexible. Building huge monolithic containers that try to do too much defeats the purpose of microservices in isolation. Having insufficient monitoring or lacking distributed tracing, you'll be totally lost when problems occur. Not automating rollouts and rollbacks. Setting inefficient resource requests and limits in your orchestrator configs, leading to wasted resources or instability. And treating containers like traditional VMs, for example, trying to run stateful databases directly inside ephemeral containers without proper external persistent storage.
Case studies are basically anyone doing microservices successfully with containers today. Kubernetes adoption is massive. Lots of stories about companies migrating from monoliths to deploying smaller services in containers. The benefits reported are consistently increased agility, better fault isolation, independent scaling. But the challenges are also consistently reported. The complexity of distributed systems, the need for skilled teams, the significant monitoring overhead.
This pattern, service per container, enabled by containerization and orchestration, really is the current standard for building and deploying microservices architectures. But the sources are very clear. Successful adoption isn't just about flipping a switch. It requires a serious commitment to automation, tooling, and building up the necessary operational expertise within your organization.
Wow, okay, we have definitely covered a huge amount of ground today, really digging deep into how modern software gets built and critically deployed. From those foundational ideas like immutable infrastructure and IAC, right through to the isolation you get with service per container and all the strategies: rolling update, blue-green, canary, for actually getting code out there safely.
Yeah, it's a lot, but understanding these patterns is just so vital now.
Oh.
Knowing the trade-offs between, say, the foundational IAC, the strong isolation service per container, the risk management of blue-green versus canary, or the simple reliability of a rolling update. It's crucial for anyone building or running systems in the cloud. As the sources really lay out, each pattern has its place, its pros, its cons. Choosing requires thinking carefully about your application, your team's capabilities, and what your business actually needs.
It really drives home that the joy of architecture isn't just about drawing diagrams on a whiteboard, is it? It's deeply connected to how things actually operate, the strategies we use to deliver value to users reliably and safely, especially at scale.
Precisely.
Yeah.
And maybe the most provocative thought to leave you with, something the source material really hammers on. Adopting these powerful patterns like IAC or immutable infrastructure. It's not just about installing some new tools or using a different cloud service. It fundamentally requires, and often forces, a significant cultural shift within your teams, within your whole organization. It demands embracing automation, breaking down silos for shared responsibility between dev and ops, and fostering a culture of continuous learning. The tool's enabled to change, sure, but it's the people, the mindset shift, that really unlocks the transformation and makes these patterns deliver on their promise.
That is a perfect point to chew on as you think about your own systems and teams. Thank you so much for joining us for this deep dive. We really hope you feel a bit more equipped, maybe even inspired, to look closely at the patterns driving your own deployments. Stay tuned for future episodes and keep exploring the fascinating world of software architecture with us. And hey, make sure you're subscribed to Joy of Architecture wherever you get your podcasts.